day of the second week of the school. And so Pedro Ferreira is going to give the second lecture on beyond LambdaCDM models. Go ahead, Pedro.
Thank you. Let me share screen. And I'm going to try and, I read up that this is what I was supposed to do if I wanted a laser pointer. Okay, spotlight like this. So you see a red dot now?
I see the red dot, the laser pointer, yes.
Beautiful. Okay, so we begin. What I did yesterday was kind of explain what I mean by beyond LambdaCDM, and it can mean many things, and there are many families and many tribes working on different aspects which go beyond general relativity plus a cosmological constant plus cold dark matter plus homogeneity and isotropy. I've decided to focus on extensions to general relativity. And I started by trying to say why we shouldn't extend general relativity. I then moved on to say, well, if we did, why we might extend general relativity. And then I showed probably the simplest case, which is just adding one scalar degree of freedom to the system and see how you might do that. And I did that by first considering like the grandmother of modified gravity theories, the grandmother of extensions, which is Jordan Brans-Dicke, and it kind of shows a lot of the aspects that you see when you try to extend general relativity. I then showed how, well, if you want to go down that route of adding in a scalar, what else you could do. And I said, if you want to keep second order equations of motion, there are games that you can play and you push it forward and you end up with something called a Hondesky action. Okay. Now, that's one particular route. There are many routes, and at the bottom of this transparency here, you will see that I have a report, a physics report that I wrote almost 10 years ago, which is a huge compilation of many different approaches to extending gravity. Okay, and if you really want to go and learn about the different approaches, you could do that. I'm just going to focus on a few other ways of doing it, just because they've been immensely popular and they crop up a lot in the literature and in what people are trying to constrain nowadays. And so I think I would be remiss if I didn't look at theories in higher dimensions. And I'm not going to go into the history of this. We know that they've been around for many decades, from beginning with Kaluza and Klein. They're part of string theory, supergravity. There are many motivations for us to look at higher dimensions. And why would one consider such a theory in higher dimensions an extension to general relativity? Well, it's an extension to general relativity in the sense that it modifies what we consider to be gravity in 4 dimensions, okay? Remember that Lovelock's theorem had this thing, which is in 4 dimensions, local, dependent on a metric, second order equations of motion, you get the Einstein-Hilbert action. One of the assumptions was 4 dimensions. Let's see what happens in 5 dimensions. And this is all going to be very schematic. So imagine you live in 5 dimensions and your coordinates on this 5-dimensional space are this capital X with an index A, and this A goes from 0 to 4, okay? That means that there are 5 coordinates. And you can always rewrite it as small x alpha, where this alpha goes from 0 to 3, so this is the 4-dimensional spacetime, plus this extra coordinate Z, okay? And the metric on this 5-dimensional spacetime is given by this gamma, all right? And we're going to simplify our lives, and this is what has always been done. This is the textbook stuff. We're going to take our metric and we're going to look at this 5th coordinate and we're going to compactify it. In other words, we're going to say that the value of the metric at Z is the same as the value of the metric at Z plus L. This is basically equivalent to compactifying this extra dimension on a circle, all right? So imagine that we had 2 dimensions, 1 dimension, 1 real dimension, and this extra dimension. We would be compactifying this extra dimension, and so we'd be living on a cylinder, all right? And on this, so if we live on this compact extra dimension, we can then do the following thing. We can do a Fourier transform, and we get a Fourier series of this metric if we Fourier transform on Z, and we have the frequencies, and the frequencies are given by n over L, okay? And it turns out that what you seem to obtain is you seem to obtain an infinite tower of fields of gamma ABs, depending on the index L. And it turns out that if you look at these in more detail, you can interpret these frequencies as the masses of these fields. And so if your dimension is very compact, this L is very small, the masses are very high. And so you can push the dynamics of these fields, the masses of these fields, to be very high compared to the energy scales what you're looking at. Okay, so that's the first thing to consider. But let's go further. Let's take this metric and let's look at it just let's write it down as a matrix. Okay, and so you have the 4 dimensions over here, the gamma mu nu, and then you have the cross term between the 4 dimensions and the 5th dimensions here, and then you have the 5th dimension here. And then you can pick a particular parameterization, which is as follows. You can get your 4x4 bit, and you can say that it's equal to a 4x4 metric times some scalar, plus some particular combination of a product of 2 4 vectors times the exponential of the scalar. Okay, so that's this bit here. It has exactly the right symmetry properties. Then you can do the same thing with the off diagonal bits, this bit here, and now it'll be a 4 vector, and you can multiply it by the scalar. And then the last bit will be this one function here, and we say it's just a function of the scalar. All right. And so now suppose we take our 5-dimensional Ricci scalar, all right, on our 5-dimensional space. So this is D5. Okay. We can factorize our 5-dimensional space into this compact dimension here and this dimension here. Okay, and we can expand the Ricci scalar, the 5-dimensional Ricci scalar, and what you end up with beautifully is you end up with the 4-dimensional Ricci scalar. You end up with a kinetic term for the scalar field, and you end up with this extra bit here, which is just the this you recognize as the action from an electromagnetic field or a U1 field multiplied by a function of the scalar. All right. So it's remarkable that when you go from 5 to 4 dimensions, it just becomes this, right? It becomes a theory with it looks just like GR with these extra terms. Now, as I said, if we compactify and make that dimension small, right? And we throw away those higher terms, so we only keep the n equals 0 term. Well, this integral is very simple. It's just going to be L over this. And that means that we get this L over 16 pi G5 because we've got rid of all the Z dependence here. And this is basically a rescaling of the Newtonian constant. So the 4-dimensional Newton's constant is going to be the 5th-dimensional Newton's constant divided by L. And what you find is if you solve the Einstein field equations and look at the non-relativistic limit and look at the Newtonian limit, what you find is that your Newtonian potential for large R's, it doesn't really see the extra dimension. And if it doesn't see the extra dimension, it just goes as 1 over R, which is exactly what you get in 4 dimension. But for small R's, for small distances on small scales, it goes as 1 over R squared. If you solve for the Poisson equation in 5 dimensions, this is what you get. So you get this transition in the behavior from large R to small r. Okay. Now this was always the canonical story of extra dimensions, but in the late 90s there was a real explosion of activity when people started reconsidering the possibility of extra dimensions and the idea that you could solve the hierarchy problem with extra dimensions. And one of the things that really emerged out of the superstring revolution of the mid-1990s was the idea that there were these extended objects that played a fundamental role in string theory. And one of the possibilities is that we live on one of these fundamental objects. What do I mean by that? I mean that we live on a 3-dimensional brain, so a 3-dimensional spatial brain in a higher dimensional space. And then we can consider what actions we might consider in such a situation. So here again, I have 5-dimensional space, okay, with a 5-dimensional Planck mass. Now I'm talking about Planck's mass. This is our 5-dimensional space, all right? And then I add another term. I add a term which lies on a 3-dimensional, a 3 plus 1 dimensional space. Let me call it a delta M, which is a brane. And this brane has some tension. And you can define a length scale in terms of the two of the fundamental constants here, this and this, which is given by L. And you can solve for this. And if you solve for this, you find a very interesting metric. This is a kind of the 4-dimensional part of the metric, okay? And then this is the 5th dimension. And what you find is that even though, so this is known as one of the Randall Syndrome metrics, okay? What you have is that you live on this brain, okay? And as you move away from the brain, the volume shrinks, the volume reduces. So even though you might have, a Z might have infinite extent in the plus and minus direction, the metric is such that it squashes the volume, so it goes to 0. So in practice, you can live in infinite dimension, in infinite extra dimension. Your extra dimension can be infinitely big, yet you will be confined in onto this 4-dimensional brain. Okay, and so this was a real revolution when people started thinking this way. And kind of the archetypal theory, and the only reason I'm mentioning this is because this comes up again and again if you look at attempts at constraining general relativity in cosmology, is a model by Valli, Gabadazzi, and Porati. And so the idea there is very similar. So again, what you have there is you have your Einstein 5-dimensional Einstein-Hilbert action on the in 5 dimensions, okay? And then you have something on the brain, but now instead of just giving it attention, okay, just this term here, we add dynamics to that brain, okay? We add the 4-dimensional Ricci curvature and the 5-dimensional extrinsic curvature to the action, okay? And it just turns out that if you work out the equations of motion, a new length scale comes in here, and the new length scale is now 1 over RC is the 5th dimensional Planck mass cubed over the 4th dimensional Planck mass squared. And now what you have is you have a deviation on large scales. In other words, on small scales, it goes as 1 over R, and it's just 4-dimensional. But once you go beyond a certain scale, you get a 1 over R squared. Now, this is really interesting, and the reason why this is interesting is if you were to try and solve the cosmological constant problem if you were to try and find some way of modifying gravity on very large scales to, for example, explain the accelerated expansion, you would want these modifications to kick in on large scales, and this is exactly what this is doing. Now, this theory has lots of problems, but at least you know this is something that is still, people still look at this because it's kind of the example, the example of the higher dimensional theory. So let's park that. That was extra dimensions. Let's consider something else now. You'll remember when I told you about Sakharov's neat idea, okay? And let me just remind you, the idea was that you would construct an action where G wasn't dynamical, you'd integrate out an extra degree of freedom and a scalar field, and you would generate all these higher order scalars invariants of R, okay? And they're all higher derivative terms. And I also told you that the corrections, why should we worry about this? We shouldn't really worry about this at low energies because the corrections only kick in when R is of order the Planck mass, if we assume that these A's are all of order unity, these coefficients are of order unity. And a notable example of that is possibly the most successful model of inflation, which you'll probably be hearing about in the other lectures, which is Starobinsky inflation. In Starobinsky inflation, you have R, and then you want to have 1 over a scale times R squared, okay? So you'd expect something like this to become important at early times. But really what we're interested in is what happens if something like this happen at late times. And so I'm just going to give you a toy model which doesn't work, but it has characteristics which would, it has some of the characteristics that you would want. So consider the following action. Imagine that you have an action where you have an Einstein-Hilbert term, and then you have a term which is the appropriate dimensions over some power of the Ricci scalar to the n, okay? And so what would happen as the universe is expanding, R, which is basically proportional to H, goes down in time. So this becomes smaller and smaller, and at late times, this starts to dominate, okay? Now, this was an idea that was put forward almost 20 years ago by a bunch of people. This was just a toy model. It has obvious problems. For example, what is the vacuum state? It has no vacuum state if you think about it, because, well, it doesn't have Minkowski as a vacuum state, because at r equals 0, this is singular. But it gives you the general feel of what you might want to do building a model like this. Now, you could generalize this. And if you generalize this, you could say, well, instead of just having the Ricci scalar here, we could have a function of the Ricci scalar. And the thing that might worry you is the same thing that worried you before about the Sakharov action, which is you have higher derivatives. You have that, for example, you have r squared. Suppose that we Taylor expand this, you would have r squared goes a del g squared g. So this is of a fourth order. You don't want that to happen. Well, it turns out that there's something very nice that happens with f of r, which was mentioned in one of the questions asked by one of your colleagues yesterday, which is that we can map it onto scalar tensor theories. In other words, our worry about having these higher order derivatives, which means that the equations of motion might be more than second order, which means that there might be instabilities, doesn't happen for f of r. And the way to see this is doing the following. Let me just define f sub r as the derivative of f. F is a function of r, so this actually should be a full derivative of f with regards to r, right? So this, you take our function f of r and take one derivative, all right? The equations of motion for f of r gravity look like this, okay? You've got these f of r's popping up all over the place, all right? Now, we can play a game. We can do a conformal transformation, and we can say that phi, let's just define a scalar field phi to be square root of 3 over kappa, where kappa is some coupling constant, some dimensional coupling constant, some coupling constant, times the logarithm of f of r. And then we do the following conformal transformation. We define g bar to be f of r times g mu mu, okay? And if we do that, it's quite remarkable that the equations, these equations transform to the following. They become r bar, they become this. And what is this? This thing here is nothing more than the Einstein tensor for the g bar. And then we end up with something like this, which looks just like a, it's just a scalar field it's just a scalar, this energy to momentum tensor of a scalar field plus some, the source, the energy momentum here, okay? And we can construct this potential here out of r f of r. So you know what phi is in terms of log of f of r. You can rebuild all of this in terms of phi. So you basically construct a potential for phi. And so again, you get a scalar tensor theory. Okay, so if it's a scalar tensor theory, we don't have a problem, right? Because we know that here we have the second order equations for the metric, and we have the second order equations for the scalar field, and everything is fine. Now, there are other examples, and I'm not going to mention them. There's Einstein ether theory, i.e. we have a 4-vector, and they're vector tensor theories, and so that's a kind of a niche area where some people have worked on. There's an area that was very hot in the mid-2010s, which is massive gravity, and again, there were questions yesterday alluding to this, which is, what if you want to give a mass to the graviton? How would you do it? It's straightforward to do this at linear level, but has problems. It's very hard to do this at non-linear levels, but you can do it now. And there are consistent theories of a massive graviton, which have other problems, but it can be done. You can break another of the assumptions in Lovelock's theorem, which is locality. There are attempts at constructing non-local theories of gravity. All of this is very speculative and interesting. Generally, the thing that I want to point out is that generally they can be mapped onto scalar tensor gravity. Not always, but generally, in many of these cases, parts of the sectors or a lot of the sectors or the important part of the sector can be mapped onto scalar tensor gravity. So it's a good rule of thumb to learn what happens with scalar tensor gravity before you tackle anything else. So let me just summarize this bit. So violating Lovelock's theorem, you can explore extensions to general relativity, and scalar tensor theory is the most studied and popular, and in some sense, I would say, in some sense, more general approach to modifying gravity. But f of r, you can also do it, and it can be mapped onto scalar tensor theory. There are other candidates. I think one of the main points I want to make is that extensions to general relativity generally mean two things. They generally mean that there are extra degrees of freedom that you need to consider. And first of all, either a scalar field or vector fields or whatever. And this is a key point in what I'm going to do next, it involves new forces and new fifth forces. And so these are the things to look for if you want to look for extensions of general relativity. Very good. Now I'm going to exit full screen here, and then I'm going to start it again. Before I do that, are there any questions I can answer now? All right, I have questions. I have questions in the chat. Sorry if I missed something. How to expand the fifth dimensional Ricci tensor, Ricci scale in terms of four-dimensional Ricci? No, you haven't missed it because obviously I don't have time to do that in my lecture. I recommend that you look up the physics report that I mentioned in my transparencies. When defining the field phi in terms of the function f of r, this field can be treated as independent of g mu nu, even if it depends on it. Yes, and that is exactly the trick. I mean, one way of thinking about it is, imagine that you have a system which has a higher derivatives. You can always go away and call the higher the derivative. Well, imagine that you have a second order system, right? You can convert it into two first order systems, right? You can convert it, imagine you have a system with q and q dot. You can redefine q dot as something else like p, okay? And these two variables are completely independent of each other, but they're intertwined in the equations of motion. What is the status of the equivalent principle in all these theories? That's a really complicated question. I'm not sure what you mean by that. It depends on what, if you go, it depends on what frame you are. It depends on whether you're talking about the weak equivalence principle, the strong equivalence principle. Again, I suggest you look at my physics reports to look at what we talk about, what we say there. What about theories with torsion? Very good question. I have always shied away from theories with torsion, although I think they're very interesting. And so there's a whole family of theories where you introduce torsion. Almost all the theories that I've been talking about, are torsion free, but you can extend it further and look at it with theories with torsion. I know very little about those theories, but I think they're very interesting. Okay, why is there less interest in F of R theories now comparing to 5 years earlier? Well, as I will show in one of my lectures, basically I think they've been the F of R theories of interest have been ruled out as theories of astrophysical interest. Basically, let's wait to that lecture, but they're not cosmologically relevant. So is it true that any single field scalar field model can be rewritten as F of R gravity? No. Another question. This extra degrees of freedom correspond to the new initial conditions because these are of higher order. I'm not sure I understand this question, but I think what you're saying is, in some sense, what I was saying with my example of Q and Q dot, right? With Q and Q dot, you rename Q dot as P, right? And so if you have second order equations of motion, you can convert them to two first order equations of motion. So you're taking one of these higher derivative terms, redefining them, and you're bringing the order of the differential equation down. Okay, that is that. Let me okay, full screen mode. Very good. Okay, so at the end of the last series of presentations I've been making, I emphasize that one of the hallmarks of trying to extend gravity is that you introduce new forces, new fifth forces, and more I think that is the way. If we're going to think about how to test these theories, that is the way to do this. You've got to think of these as theories of fifth forces, and you have to think of way of looking for these fifth forces. Okay. Now that's quite interesting because there are extensive tests of fifth forces. and extensive tests of how fifth force, how, for example, the Newtonian theory of gravity or Newtonian forces modify. And we know there are incredibly tight constraints. As I mentioned in the introduction, if this is an interesting plot, and so before I say anything, let me just explain what this plot is. On this plot, what I have on the x-axis is the local gravitational potential of a system, okay? And then on the y-axis, I have the local curvature of a system, all right? And what I'm putting down here very schematically, and there's a much more detailed plot of this in this paper that I have down here, I'm laying down different regimes where gravity is tested. So over here, I've called this PPN for parametrized post-Newtonian. But what I mean by that is this is kind of our local environment. What I mean here is tests in the solar system, tests actually with millisecond pulsars, tests in the lab. They're all over here. And they are very constrained. The constraints on gravity are phenomenal over here, all right? So they lie in this regime of curvature and potential. Where we've entered over the last 5 years, this incredible new regime with LIGO and the Event Horizon Telescope, where we're up at the boundary where we start to test systems where the local potential is of order 1. As you remember from your GR, you know, at the horizon of a black hole, phi is of order 1. Okay, so it's not really strong gravity, but it's close to of order 1, and we're beginning to test here. And you know, we don't really have any tests yet of significant tests of general relativity here, but we'll be able to test it here. Cosmology lies down here. Okay, cosmology lies down the local potentials around here, but very low curvature. And so you can see that these different systems pro-gravity in completely different regimes. And so you could ask yourselves, what if I test something here? Does that mean that I've tested it here? And what I'm going to explain is actually not necessarily that a phenomenon called gravitational screening can mean that you do tests over here and that you find things are just behave as you'd expect in GR, but over here they might not. So that's kind of the motivation for what I'm doing next. But before I do that, let me just give you a kind of a cartoon description of a fifth force. And the way I'm going to do this is just say that a fifth force typically has this form, okay? It has a gravitational potential. This is 5 for fifth force, not the 5 dimensions. It has an amplitude, let me call it g squared. It'll depend on the mass of the object, okay? And then there will be a range, the range of the fifth force, okay? And so this is what's known as a Yukawa force. So if this is going to be small, we either have to have that the amplitude is very small, okay? In other words, that the amplitude goes to 0, or that the range is very short, which means that the mass has to be very large. If you see, if I push this m to be very large, very rapidly, this becomes very big, and this is going to be 0, okay? So that's 2 ways of suppressing a fifth force, by either suppressing this bit or that bit, okay? And how does a fifth force come into all this? And I'm just going to remind you of this calculation that I went over yesterday. This is, we know what the geodesic equation of a particle is in a metric g, right? And now imagine that the metric that it's been coupled to, remember when we did that transformation and we moved into the Einstein frame, that metric was actually a product of this conformal term times the original metric, okay? So let's do something very simple. Let's just take this conformal term and just do a linear expansion, assume that this phi is very small, okay? So what we have is that the metric that feeds into the geodesic equation is going to have this extra correction in. And so to work this out, we know that this the Christoffel symbol is going to be g tilde minus 1 del g, and we need del g here. The del g is going to pick up in Minkowski space. Let's focus on Minkowski space. Is going to pick up this phi, so we get this gradient of phi here. Okay, so this thing is going to pick up this gradient of phi here. So now if we plug all this into here in Minkowski space, what do we get? Well, on the left-hand side, we've got the acceleration here. And on the right-hand side, we're going to get these gradients of phi, okay? we're going to get these gradients of phi. If we look at a simple static spherically symmetric case, the equations of motion look like this. We have that the acceleration, the radial acceleration, is simply going to be a source by the gradient of phi. It looks exactly like a force. This force is just the gradient of phi with a coupling constant here. Okay, so that's why we say it's a fifth force, that modifying gravity in this way actually is equivalent. If you try and make all the rest look the same, it's equivalent to adding in a fifth force to the system. Now, what does this fifth force look like? Let's just up the ante a little bit. Suppose you have an action for a scalar field, okay, and you have the scalar field, and it's got a kinetic term, it's got a massive term, and then you've got the coupling to matter. And as I said, we're in the Einstein frame now, so it's non-minimally coupled. We've got this correction here. And we now look at the equations of motion of this, and it's the Klein-Gordon equation. And so this is just a massive Klein-Gordon equation here. And then we have this bit here because of the coupling to phi here, okay? And you solve for this, you can work this out, and what you end up, and there should be an equals to 0 here, which I've somehow disappeared. You get the Klein-Gordon equation sourced by T mu, right? The trace of the energy momentum tensor. Okay, so this is what comes from this action here, and we saw this already when I mentioned Jordan Brans-Dickey, and it's kind of a general feature of these scalar tensor theories. Okay, so now if we assume a static spherical symmetry, so we have that it's just let's assume a really simple thing. Let's assume a point source at 0, okay, with a mass mc. We know how to solve these equations, and we're going to take the regular solution, the solution that goes to 0 at infinity, okay, and we solve it, and it has to satisfy the boundary condition at 0. So that fixes this a over here to be minus alpha mc over 8 pi. And then we can take the derivative of that thing, and we end up with alpha squared mc over 8 pi r squared. So this is 1 over r squared, just like Newtonian gravity, plus this Yukawa term, plus the bit that comes from taking the derivative of this, okay? So this is what you get. This is the fifth force that you get from a coupling of this sort, okay? Now, we have remarkable constraints on them. This is a review by Adelberger and collaborators, which we keep on showing in this topic. And what you have here on the y-axis is you have the strength of the fifth force, which is the g squared or the alpha squared in the previous transparency. And you have on the x-axis, you have the scale. And so here is laboratory experiments, okay? And what you have here are this dimensional coupling constant is we have that it's around, these are the ranges of the constraints that you have, okay? And as you go to smaller and smaller scale, larger and larger scales, you get better and better constraints. And what is interesting is when you jump over to here, to this one, where you start using large scale constraints, all right? So you start with from centimeters, but all the way up to planetary and astronomical units. And what you see is that you get incredibly tight constraints on these fifth forces, okay? So the way to really constrain fifth forces is on large scales. That's where we're really seeing remarkable constraints on large scales. But the point also to take away from this is that we have really tight constraints on fifth forces. In other words, we do not see fifth forces on very large scales. And by large scales, I mean on planetary scales, okay? Cosmology would be out here. So why look at these extensions to general relativity if the data on large scales, and by large scales, I mean solar system scales, is already indicating that, there are no fifth forces? Well, the idea is that fifth forces aren't that simple, that a constraint on a fifth force in one regime is not the same as the constraint of a fifth force in another regime. In other words, the environment affects the strength or range of the fifth force. Now, a key point that I want to make is that this is not an add-on. In other words, the fact that fifth forces depend on the environment is not an additional complication that you add on to try and fix the problem of them not being detected on small scales. It's actually an inherent part of many theories. And I have to be honest, for many years, I felt that it was an add-on, but having looked at it in more detail, what you find is many attempts at constructing a scalar tensor theory inevitably have this property of gravitational screening. So let me explain what that is. And what I'm going to do is I'm really going to focus on mostly on one, but mention another. form of screening. I'm going to focus on chameleon screening. Okay, so let's look at, again, same type of action. This is a scalar field action. This is a Einstein frame. You have here the Einstein-Hilbert term, you have the kinetic energy, you have the potential, and then you have the non-minimal coupling to matter, okay? And again, just to remind you, this G tilde is some conformal term times G alpha beta. I say, let's look in the weak field regime, so 1 plus alpha phi here, and I'm just going to rewrite it as 2 phi over m, okay? And now, if I redo the calculation, I get an equation which you've already seen, which is box phi, because now I'm considering a general potential, so it's going to be v prime phi plus the non-minimal coupling to the potential, to the stress energy tensor. Now let's look at what happens for very small phi. And if a very small phi, what you have is that your equation is box phi equals v prime plus lambda m gamma over m, right? So that's your, in some sense, it's the derivative of your effective potential. And your effective potential looks like this, really. It's v phi plus rho phi over m, okay? But what does that look like? Well, imagine that you have a potential which goes as phi to the n, but where n is negative, all right? So your v of phi falls like that, okay? And then you've got this gamma of your density times phi over n, right? That goes like this. What you have is that your effective potential has a minimum, and the minimum is over here. But what is interesting is this minimum is going to depend on this rho. If you change this rho here, okay, if this rho was larger, the minimum would happen over here. If this rho was smaller, this curve would come down here, and the minimum would lie over here. In other words, the minimum depends on the value of rho, okay? And so I have here phi minimum. There's a minus here, remember, because n is negative, all right? Now, let's look at fluctuations around this background, okay? Fluctuations around this background, well, there should be two derivatives here. You want to look at basically the value of the curvature around that minimum. And so you m squared phi, is going to be v double prime of the effective potential. Sorry, double prime of the effective potential, and you can get an expression. And so that effective mass is going to depend on the density. But this is quite remarkable because this means that effective mass depends on the density of the environment. And what is this effective mass? This effective mass is nothing more than the range of the fifth force of that scalar field. And so what you have is for high values of the energy density, your mass is high, so it's very short range, so it's suppressed. But for the low values of the density, that value is small, and so it's long range. So already you can get a qualitative picture of what will happen in such a situation. What you'll have is that in regions of high density, the fifth force is completely suppressed and you can ignore it, and just Newtonian gravity is valid. But in regions of very low density, or for round objects which have, are small, that m squared is going to be small, which means that you'll have this extra fifth force. Depending on what objects in the environment that you look at, you will have or you might not have this fifth force. Okay. So let's just build some solutions. And so the first thing I'm going to do is I'm going to consider a really simple solution. This is the density here. This is the R coordinate, okay? And I'm just going to consider a constant density rho c out to a value RC. Now, far away from here, we have that the scalar field is settled at some value, phi infinity. And so the mass of the scalar field is just set by the second derivative of the effective potential at infinity, all right? It's going to be some value, and it's going to be presumably small because the density is 0 or non-existent at infinity, okay? Now let's consider a small object here. If we put a small object here, phi will be a small perturbation around that asymptotic value, okay? Which means that the effective potential is effectively rho c phi over m, okay? And so if we do that, we can solve it, and we can solve for it. And what we find is that inside the object, we have that I mean, this is the kind of thing you've done if you've done electromagnetism, right? The phi is going to grow from some value from the middle outwards, or it's going to go from MC to phi infinity, and then you're going to have a term outside which has this constant term over here, and then it's going to decay. It's going to have a Yukawa-like potential here, 1 over r and an E minus m. And what you find is that these two match at RC, so these are consistent. Now, as I said, if m phi is small, right? If m phi is small, this is small, so it's long range, and so your f will be this term here will be Newtonian. In other words, you'll have a fifth force which competes with your Newtonian gravity, and in other words, it might be observable. Okay, so this is what we call unscreened. This force will be unscreened. Okay. But now let's consider an object with high density, okay? And then the situation is different. So again, we have an object which goes out to RC, and it has a certain density, but now the density is high, and the density is so high that inside the object, deep inside the object, the scalar field has a completely different minimum, okay? Let me call it phi c, okay? While out at infinity, it has the phi infinity that I told you before, which corresponded to the small Yukawa mass, all right? But now we have to be careful because there has to be a transition between phi c and phi infinity. And so we have to have this transition. And so we have to define a new length scale S, which lies inside the size of the object, okay? And we have that inside this object, inside here, we have phi c, okay? Then we have a transition regime, and we know that the solution is going to be something like that in that transition regime. And then outside, we already know what the solution is like. And so now the game is we need to match all these things. We need to match these constants, C, D, and A, but also S, this thing over here, okay? We need to match all these things. And I leave it as an exercise, but what you do, if you do that, you find a number of very interesting things. The first thing you find is that if rho c is sufficiently high, you'll find that transition regime is narrow. It's thin. It's basically a thin shell. Okay. You find that RC minus S. Let me remind you what that means. That means that RC minus S over RC. This thing is very thin. Okay. And what you also find is that F phi, i.e., the value of the amplitude of the fifth force, asymptotic fifth force over the Newtonian fifth force, given that this thing is basically 0, so we just have to compare the 1 over r terms, goes to something like this, and this is very small as well. And so what you find is that your fifth force is suppressed. In other words, near heavy objects and dense objects, we have that the fifth force is screened. So you can actually work this out, and it's an interesting exercise, and you just have to pull back. You just remind yourselves a little bit of your solving your PDEs and your electromagnetism. You can show that close to a small object, this scalar force is unscreened, but near a large object, it is screened. And this has, in practice, this is quite far-reaching consequences, which we will look at in one of the next lectures. First of all, that in dense objects we don't see a fifth force. In other words, if we're in a galaxy or in clusters where you have a certain overdensity, you have a certain accumulation of mass, you shouldn't expect to see this fifth force. So you shouldn't expect to see deviations from a Newtonian gravity. Near dense objects, we don't see this fifth force. So if we're near a star or near a compact object like a neutron star or something like that, we shouldn't see deviations from Newtonian gravity. We should see this fifth force should be suppressed. But if we're looking at diffuse material, we might feel the fifth force. So for example, if we look at the gas that surrounds a galaxy, and suppose that this galaxy is in a low density environment, we might see it. If we look at dark matter halos, again, in the right environment, this is quite a diffuse object. We might be able to see it. And of course, if we look at empty regions of space, and somehow we're able to monitor test particles there, or test objects there, if, for example, in voids, we might be able to see fifth forces. So this already gives us an indication of where we might go and look for these signatures of these fifth forces, which are signatures of these extra fields, these extra degrees of freedom. Okay. I also want to mention, so I've mentioned chameleon gravity, and chameleon gravity, chameleon screening. I want to mention another pretty important form of screening, which is called Weinstein screening. And Weinstein screening really emerged when people were thinking about massive gravity, giving a massive graviton in the 1970s. But it's been shown to appear in lots of different theories. For example, when I mentioned yesterday Galilean theories, Galileans are endowed with this kind of screening mechanism. So let me use a toy example. Let me look at this. This is known as the cubic Galilean, okay? And the cubic Galilean looks like this. You have the action has this kinetic term here, and then it has this new term here, which is box phi, del phi, but it's all tuned in such a way that, you don't get higher orders equation of motion, okay? And again, it'll have a coupling such that you has a coupling to the energy momentum, to the energy momentum tensor, okay? Now you can follow exactly the procedure that I followed before. You can work out the equations of motion, okay? You can put a particle at 0 with a mass mc, and then you'll have a set of equations of motion. And the only trick I'm going to give you for you to solve this is you can parameterize your derivative of phi r. Your equations will only have derivatives of phi r. That's one of the interesting things that you'll find. But your derivative phi r, you can parameterize it as the product of the Newtonian force times some function g of r, okay? And you can solve it, and you can actually solve it, and it's in an algebraically. And you solve it algebraically, and what you find is that you find a new length scale comes in, and this length scale is a function of C3, this constant here, the mass of the object, the lambda, which is this coupling, the dimension 4 coupling here, or length scale here, or energy scale, and the mass of the coupling to energy momentum. So you bundle all these terms up into this, and it defines a length scale. This is what is known as the Weinstein radius. And what you find is that on scales smaller than the Weinstein radius, inside the Weinstein radius, this g of r goes to 0 as basically r to the 3/2, okay? Which means that this is the fifth force, remember, this is the fifth force. It will be suppressed relative to the Newtonian force. And so what you have is near a massive object in these theories, the fifth force is suppressed relative to Newtonian gravity. But if you go sufficiently far away outside the Weinstein radius, it's not suppressed. So this is a really neat calculation that I suggest you do. It's a really good exercise to work it out from that action. I actually don't need to give you more than just this for you to work it out. Okay, so this is another mechanism in which you have screening. So let me just quickly summarize. We have that extra fields generally lead to fifth forces. And this is a point that it took me a while to just absorb this. It's a really important fact. If you want to study extensions to gravity, it really means thinking about fifth forces. We know that fifth forces are very well constrained in certain regimes. Nevertheless, there are what one might call natural mechanisms to suppress them. And this is what's known as screening or gravitational screening. One example is chameleon screening. What you have there is that the environment or the density is what screens the object. And we worked out an example there of what happens with objects of a certain size and density. Another example is Weinstein screening. Okay, so let me stop there. And I'm tempted to stop my lectures here for today and try and answer questions, given that I'm only going to be around for half an hour at the Q&A. Okay, let me try and catch up with the questions. Okay, how do the screening of the fifth force translate to new particle? Is it just a zero spin particle for phi? So what I'm talking about, this is a good question, and I'm going to give you a bunch of answers. The first answer, well, first of all, yes, this is a fifth force. This is a fifth force, and I've only been looking at spin zero particles, so you can think of it as a spin zero particle. This effect that I'm talking about is a non-linear classical effect. Okay, so I do not know how this would manifest, how you'd even start thinking about this in a quantum mechanical way. If you think of a particle with a mass, right, you solve the Klein-Gordon equation. The Klein-Gordon equation has a propagator, which is 1 over k squared plus m squared. Here, this m squared is environment dependent. So I don't even know how you would go about doing this. It's an interesting question. I don't know how to answer it. Oh, okay, I think I've answered your question. Then, I would like to ask if there will a list with all these exercises on the website of the school. No, unfortunately not. I'm really sorry. Then, you said that near compact objects, there is no fifth force. So how could you explain the attempt to see deviations of GR near compact objects using scalar Hare spontaneous scalarization mechanisms? No, excellent question. So the question is, why, if I say theories are screened near compact objects, why are people looking for deviations of gravity near compact objects? Okay. If I have time, my hope is to actually go into this in more detail. What I'm saying is screening appears in many theories. It's quite a general phenomenon. There are theories that are not screened. And if you look at the theories where people are looking in detail about scalar Hare around compact objects, they're looking at particular theories like Dilaton-Gauss-Bonnet or Chern-Simons, dynamical Chern-Simons. These theories aren't screened, okay? These theories have particular properties which actually make them of no interest whatsoever for cosmology, which is the focus of this school. Nevertheless, they are of interest, and my hope is in the last lecture I will mention them as a counterpart to the family of theories that one is looking at here. Since no fields lead to fifth forces in general, so new fields lead to fifth forces in general, can constraints to fifth forces be treated as constraints to inflaton fields? I don't think so, because they're completely different regimes, completely different energy scales. I'm really focusing in these lectures on physics, which might be observable at late times and which might affect the late time dynamics. If you look at the type of fields that affect inflation, we're talking about fields with energy scales and masses which are many orders of magnitude higher than what we're doing here. Okay, I am not convinced that the screening mechanism is natural, because as far as I understand, the screening depends on our choice for VFI, and it is arbitrary. We just choose it in order to the field acquire a large mass in high density environments. What am I missing? I think you're missing the point. The point is that you pick a VFI, you always have to pick a VFI, and it could be m squared, phi squared, it could be it could be something else, and often you get screening. Let me give you an example. Imagine that I took Jordan-Brans-Dicke theory and I added a mass term to the Brans-Dicke field. Simplest thing you can do. If you do that and you transform to the Einstein frame, you have screening. Simplest. That's the simplest choice you can make of a potential. Just give it a mass in the Jordan frame. So it's not a convoluted choice of Fi. What you're saying here is what I thought for years. I thought for years that you had to pick a particular type of Fi to give you screening. No, that's not the way to think about it. What happens is often the simplest of VFIs that you pick will give you screening. When you mentioned the 3D brain, was that idea taken from string theory? Essentially, yes, it was taken from string theory. I ran out of questions. Please ask. You've got 3 more minutes to ask me questions. Hi, does screening mechanism have any shape dependence, i.e. non-spherically symmetric? What if there's rotation frame dragging? Thank you. Super interesting question. You know what? It's pretty difficult to solve the equations once you go beyond the simplest scenario, okay? And over the last few years, people have started to look in more detail at how what screening is like near more complex objects, as you say, non-spherically symmetric, dynamical. For example, the simplest thing you could think of is a three-body problem with screening, you know, or even a two-body problem with screening. What happens there? So there might be all these things. It's completely open for investigation. Could the fifth force be related to dark matter gravitational pull, for instance, in galaxy rotation curves? There are attempts at doing that. And so, for example, there are relativistic versions of a theory known as MOND, which I really do not want to discuss here, in which a field plays this role. And I would direct you to the work of Konstantinos Skordis, who is by far the person who's written the best papers on this topic. Regarding to your points about screening being natural and that simple potential lead to screening, is it fair to say then that you need to pick a particular potential to avoid screening and thus no screening is less natural? Very good questions. You know what? I've never sat down and thought through this. So the question is screening natural? So is unscreening, unscreened theories unnatural? I've never sat down and just looked at the family of potentials to try and figure out what is more natural or not. All I'm saying is it's not difficult to get screening. You pick some of the simplest potentials and you get screening. I could also pick a simple potential and not get screening. So for example, if I pick lambda phi to the 4 in the Jordan frame, I don't get screening. And that's also a simple potential. So, you know, it could go both ways. What observational effects should we look for the cosmic voids to detect this fifth force? Very good question. There's a whole literature on this. I'm not going to actually address this in one of the lecture when I talk about looking for fifth forces, but I suggest I will in the Q&A I will give you a reference for somewhere where you might find this. About the 5D extension, how could we physically interpret the infinite tower of frequency massive modes? Well, I think that is a physical interpretation that you've just given. It's an infinite tower of massive modes. I mean, I don't think I could do better than what you've just done. What creates the fifth forces in the nature? I don't understand that question. It's the scalar field, so I don't understand what more I can say than that. How do we rule out these theories with screening without having observation measurements in every single regime environment? Nice question. I think what you have to try and do, well, actually, let's wait and I'll show you the kind of things that we can try and do in one of the future lectures. Is chameleon screening related to the local density or local density contrast? Would screening related to the local density necessitate the definition of a threshold density? Interesting question. Probably you'd need to define a local, you need to define a threshold density. Are there some constraints on the fifth force models from gravity waves originated in black hole mergers? Are there? No, not yet. That is one of the topics which I think is of interest. You talked about theories with higher dimensions. What about Gauss-Bonnet gravity? And is there a consistent way to have a 4D theory without breaking Lovelock theorems? You know, Gauss-Bonnet gravity depends on what you're talking about. Pure Gauss-Bonnet, there were this recent spate of papers which I think have gone away because you couldn't really do it consistently. There are, most of the activity is by adding a scalar coupling to the Gauss-Bonnet term, giving it dynamics. Can we have a same general screening for all Horndeski theories or beyond Horndeski? I think different theories have different types of screenings. Some theories have chameleon screenings, some theories have Feinstein screening. And I'm afraid I'm going to have to end here. But thank you for all those great questions.
Thank you, Pedro, and see you at the Q&A for the first half now.
Very good. I'll see you at the Q&A. Okay, bye.
Bye. So we resume in half an hour for Chiara's lecture.